In this video, we're going to be discussing a very interesting paradox on a game involving two sealed envelopes. So this paradox involves probability and expected value and has a very unexpected and surprising conclusion. So let's go ahead and get right into it. Here is our strange game here that we're going to introduce, where I offer you two sealed envelopes. I tell you that one has twice as much money as the other one, but I don't tell you which envelope is which. You choose an envelope and open it, at which point you can keep the money that you find inside it, or switch and keep the money in the other envelope. So you choose one of the envelopes at random, open it, and find $10. Should you switch envelopes or not is the question here. Which would it be more advantageous for you to do? So in order to solve this problem, we're going to need to use the principle of expected value in probability. So basically what expected value is it's the average of all the possible outcomes and their probabilities of a certain event. So the expected value formula goes something like this. Your E is the expected value. You've got the, okay, so we're going to go ahead and turn that off. So we have an E over here, which is our expected value, and in our expected value equation, we have a probability, and we're just going to have to remove that, P1 we'll call it, and that's the probability of your first possible outcome occurring. This could be like 1/2 or 2/5 or 3/8, whatever it is, your probability, and then times x1, which is the expected outcome. So what you're going to get out of that value. So if it's a coin, if it's a die roll, for example, then, for example, if you have an outcome 1, rolling a 1 on the die, your P is going to be 1/6 because there are 6 possible outcomes, and that 1 is just one of those. So 1/6 times 1, because your value is 1. That's your roll. So then you just keep adding the same thing, P2 times x2, and you're going to go all the way up to Pn, where n is the total number of outcomes, times xn. Okay, so that's our expected value equation right there. That's how you would get to an expected value for any possible event. So we're going to go ahead and fill in this equation for the envelope situation here. So first, we're going to define the expected value equation for switching envelopes, because we need to find out which has the higher average value, you switching or you not switching. Okay, so let's go ahead and write E switching envelopes. So this is going to be the expected value of you switching equals the probability of all the different outcomes. So P1, what's that going to be? So there are really only two possible outcomes here. You open the other envelope and you find $5, half of the 10, or you open the other envelope and you find $20, twice the $10. Okay, so that's a 1/2 probability that you find $5, plus another 1/2 probability that you find $20. So then you just do the math here. 1/2 times 5, that's 5/2. 1/2 times 20, that's 20/2. So you get 25/2. And that's equal to about 12.5. Okay, so that is your expected value of switching envelopes. Now, let's go ahead and compare that with your expected value of not switching. So this is going to be the expected result you're going to get if you don't do anything, if you just keep the money that you already have in the envelope. And this is pretty simple to see. You don't need to do anything here. There's no additional outcomes. So the expected value is just going to be $10 because that's the value you already have in that envelope. Pretty simple there. So right away you can see that the expected value of you switching envelopes is higher than that of you not switching. The 12.5 is in fact $2.50 higher than the expected value of you not switching. So here at face value, it would appear that you should always switch envelopes. Logically, mathematically, as we've shown right here, it looks like that's the case. However, this also doesn't follow, because it seems like you should have a 50-50 chance of either getting more money when you switch or getting less money than what you originally had. You're not losing anything here, by the way. You have $10 and you have the option to get more or get slightly less. So it seems like it would be, well, you could go either way. It doesn't matter if you switch or if you don't. Why should you care about these outcomes here? So that's what it may seem like, and in fact, if you dive a bit deeper into this envelope paradox, you'll see that this actually is the case. In fact, it doesn't matter if you switch or not, because we've made a serious error in our reasoning here with the expected value equations. So basically, let's go back to our original expected value equation up here with the e, the p's, and the x's, all of this. So our 5 here, our 20, those are the x values, the x1, the x2 for the expected value of you switching. Now, it turns out that we're using that variable x to define two different things when we compare the expected value of switching and of not switching. Because really behind the scenes in this second equation, you've only got one outcome. That's the x equals 10. And we're making assumptions here in these equations that we can't really make. Because we're saying that, okay, we're defining our value of x here to be dependent on whether or not the envelope you choose first is the one with the more money or the less money. So for example, it's dependent on whether the $10, if you're going to find a $20 envelope and the $20 in the next envelope or $5 in the next envelope. It's dependent on the value of money in the envelope you open first. Because you could have opened maybe a $500 envelope at first, and it would have been $1,250. It could be any possible value, and we're assigning the value for variable x dependent on the value of that first envelope. So basically, what we're doing here is we're making assumptions for the variable x that we can't make, and as a result, our calculations for the expected value are flawed. So if you were to go through and write a revised equation, you'd find that in fact the expected value of switching and of not switching are exactly the same. And you're not going to get a number. It's going to be in terms of x here, because if you use numbers, you're going to wind up making incorrect assumptions again. So you have to write a new equation in terms of x and p only. So it would be an equation without any constants. So that's basically the anatomy of this envelope paradox. While it may seem like you should always switch at first, upon closer inspection, you're going to find that it doesn't matter whether you switch or not, because we were making assumptions on that x variable. So this is a very interesting paradox. If you'd like to find out even more information about this, I highly encourage that you check out some math articles online from various reputable universities and sources detailing the other solution and proving why it doesn't matter if you switch or if you don't. So if you want an even more in-depth analysis, you can go ahead and check out some of those articles. But in this video, we basically went through and outlined the first possible method of discovering whether you should switch or not. We first found out that it may seem like you should switch envelopes in all situations, but in fact, it doesn't matter because of the whole x variable situation. So we basically discussed the sealed envelope paradox and a possible method for how to resolve it. This was a video about counting probability and expected value.